Linear SVC is celebrated for its simplicity and interpretability. Think about it. This model doesn't hide behind complex layers or require a PhD to understand its workings. It's approachable, making it easier for both beginners and experts to visualize how it classifies data points. In practical terms, that means stakeholders can actually see the decision boundary, making the results easy to explain and act upon. When it comes to data, less is more. Linear SVC thrives on small to medium-sized datasets, working exceptionally well when the number of features isn't overwhelming. It's like solving a puzzle with just enough pieces. It doesn't overcomplicate things. This efficiency translates to reduced training times, helping you get from data to decisions faster than more complex models. Let's talk about power versus cost. Linear SVC has lower computational complexity compared to nonlinear models, making it a perfect fit for situations where resources are limited. Its computational demands scale efficiently with the size of your data, meaning it's ideal for real-time applications where speed matters just as much as accuracy. And then there's the ever-present danger of overfitting when models become too good at memorizing the training data but fail miserably on unseen examples. Linear SVC is your defense here. Its simplicity makes it naturally robust against overfitting, especially in high-dimensional spaces. When paired with regularization techniques, it ensures that the model generalizes effectively without being tripped up by noise or irrelevant patterns. These strengths, simplicity, efficiency, low computational costs, and robustness make Linear SVC a go-to tool for tackling a wide range of classification problems. But here's the question. With all these advantages, where does it fall short? Can it handle the complexities of real-world data, or are there limitations we need to address? Stay tuned, because that's exactly what we'll uncover next. Imagine trying to separate two groups of people at a crowded party, but instead of standing on opposite sides of the room, some people are milling around in the middle, blending together. You've been given only a single piece of tape to create a straight line dividing them. No matter how hard you try, that one line can't account for the complexity of the crowd. This is exactly where Linear SVC begins to struggle. While Linear SVC is powerful for simple, linearly separable datasets, real-world data is often far more complex. One of its primary limitations is its inability to handle nonlinear patterns. It assumes that the data points can be neatly separated by a straight boundary, but in practice, datasets often exhibit curved or intertwined relationships. For example, imagine a dataset where the categories form concentric circles. There's no straight line that can separate them. In these cases, forcing a linear boundary leads to high misclassification rates and poor performance. Another significant challenge is sensitivity to outliers. Linear SVC focuses heavily on the data points closest to the boundary, the so-called support vectors. But if an outlier sits far away from the rest of the data, it can pull the decision boundary disproportionately in its direction. This means that a single extreme or irrelevant point can drastically affect the model's accuracy, making the results unreliable unless the data is carefully pre-processed to remove outliers. Then there's the issue of feature scaling. Linear SVC is highly sensitive to the scale of input features. Imagine trying to balance a seesaw where one side is loaded with tiny pebbles and the other with a single boulder. If one feature has a much larger range or magnitude than the others, the model might give it undue influence, distorting the decision boundary. Without proper scaling or normalization, Linear SVC can produce biased results that don't truly reflect the structure of the data. Finally, Linear SVC's simplicity can become a limitation in high-dimensional or noisy datasets. In these scenarios, the straightforward nature of a linear boundary might oversimplify the problem, failing to capture the subtleties or hidden relationships in the data. This can lead to underfitting, where the model is too rigid to adapt to the complexities of the real-world scenario. While Linear SVC is a robust and efficient algorithm, its assumptions about data structure and its reliance on linear boundaries make it unsuitable for every classification problem. When faced with nonlinear relationships, significant outliers, or poorly scaled features, Linear SVC can struggle to deliver the accuracy and adaptability required. But the real question is, how do we address these challenges? What tools and techniques can help us overcome these limitations and handle more complex scenarios? That's exactly what we'll dive into next.